I'm very happy to have Evelina and Dimitri for the first time in Brussels, so showing what they do and performing. So they have a very long career of artists working with science and scientists. I don't know, maybe it comes from their background because they were educated in Russia at the Soviet time, and science was quite a popular topic. They could find science magazine and so on. You couldn't find other kind of magazine, but science magazine you could find them. And then when creative people are in this scientific education, what became now, if they are artists and what they are doing, you will see it tonight. So we will do first a lecture, and then we do a small break, and then they will do their Sonolevitation performance. So, Evelina and Dimitri, up to you.
So, thank you, Yves, for the nice introduction and for inviting us here. We are very happy to be here. And we will talk tonight a little bit about our research connected to the life of sound waves and the behavior of sound. And from the very beginning, when we started working together with Dmitry, and neither of us was an artist. Initially, I was studying philosophy, and Dmitry was studying filmmaking and making films. But then we met each other, and we were doing these experiments in our free time that all of our friends were very interested in, and we decided to bring it to the public. But some of the questions that really were interesting to us were the questions of the world from the point of view of waves and fields, not from the point of view of particles.
Well, approximately a decade ago, spending hours upon hours chasing after this faint light source, a phenomenon known as sonoluminescence, little did we know that we had penetrated a Pandora's box. At the time, sonoluminescence, which is actually something that takes place when high-frequency sound waves enter a liquid, various liquids, most of which have microbubbles of gas in them, bubbles that are far too small to see, not like the ones that you encounter in beer or champagne. But when a high enough frequency, in other words, a sound wave that has a short enough wavelength can fit into these microbubbles, they begin to implode, they begin to collapse, and when they do so, the gas becomes so dense that temperatures are reached as high as are found on the sun, temperatures as high as at least 10,000 degrees Celsius, perhaps much higher. And at that moment, light is emitted, and this light takes the shape of the sound waves, and that allows us to observe sound three-dimensionally in total darkness. Yeah, it was believed at the time that we had encountered this phenomenon that perhaps even nuclear fusion could be attained just with high-frequency sound waves. So it was a very, very hot topic in physics. But in recent years, it was understood that the temperatures just weren't quite high enough. It's one thing to get to tens of thousands of degrees, and it's another to get to millions of degrees, is what you essentially need in order to cause atoms to start fusing together. And ever since then, this still unexplainable phenomenon has been abandoned by the scientific community.
As a research topic. And of course, sonoluminescence still doesn't have any practical application, which may appear in the future, and For example, Ray Kurzweil, he speculates in his book that possibly you can use the energy of sonoluminescence to power nanobots, these nanostructures that can circulate in liquid or even inside of the human body, although cavitation is quite dangerous if it happens in the human body. But this whole project, Camera Lucida, it started as an idea, as a desire to see sound waves, to see the behavior of sound in a very immediate way in a three-dimensional environment. And of course, since longest time there were numerous speculations, especially in the domain of esoteric teachings about and even the likes of Newton put this connection force, and Newton thought that the light spectrum, the way we see it broken down through the prism, is connected to the octave. So we think that there are 7 colors in the rainbow, but that was actually an idea of Isaac Newton, who took this analogy from music, and he asked his assistant to separate these different 7 colors in the rainbow, because he didn't have a very sharp eyesight by that time. So and of course there are works of Scriabin and works of various synesthetes, and synesthesia was another phenomenon which we were interested in, because it seems that synesthesia and even more intense variation of it, which is called savant, allows your brain to have incredible capacities of memory and just holding and processing much more information that is possible for normal people, just because of this some extra connections in the brain. And in some research you can find that very young children, before 1 year old, they perceive everything synesthetically. So every stimuli, be it sound or light, causes the stimulation in the areas of the brain that respond to smell and sound and light. So the very young brain doesn't divide between different types of sensations. So we wanted to tap into this primordial brain, into these capacities of the brain, and start seeing the space-time and this fabric of space-time that we believed has very strong connection to waves and fields through experiencing sound through your eyes, possibly. And of course we know from physics, from scientific research, that both light and sound are different waves, but of course they are so separate on the spectrum, and the frequencies of light are very, very high. So you need much more intense energy to create a vibration that is, I don't know, what is the frequencies of light spectrum?
Well, I mean,
7.
if you're talking about the visible spectrum, yeah, it's very high.
It's like 700,000 vibrations per second, and with sound, it's like, I don't know, 40 hertz. You're talking about 40 times per second. So you can imagine that these energies are incomparable. So to create light with a sound, with the energy of sound, is unbelievable. It seems like a miracle, and that's why a lot of scientists were thinking that yes, maybe the cold fusion is possible.
Well, most of the scientists, in fact pioneers in the field of sonoluminescence, told us that we were wasting our time, that we would never be able to see sonoluminescence at the size that we had foreseen, that we thought was appropriate for an immersive experience. And so we felt very, very lucky that when we were at this international conference on sonochemistry in Japan, when, for the first time, there was a fellow there, the director at the time of the Göttingen Physics Institute in Germany. He was a big expert in sonoluminescence, and he had faith that we would be able to actually accomplish this work. And suddenly a team of Japanese scientists appeared that helped us create the first version, which we saw here. In fact, we wanted to build a sphere in the first place, but the Japanese scientists told us that, oh, you'll never be able to create sonoluminescence in the sphere. You'll never be able to create a standing wave, which is the way that they're used to looking at it. In fact, they're used to looking at just one single microbubble in a very tiny cuvette. And we, of course, would prefer to look at hundreds of thousands of these microbubbles in a very large liquid environment.
So what you see on this image here, you can kind of trace a standing wave and even see the wavelengths of sound here. So these streaks that are not very orderly, but you sort of can see these parallel lines, and these are the standing waves that you can observe. And in fact, the performance Sonolevitation that we'll show later tonight, it's also based on the phenomenon of a standing wave. And they thought that yes, in a spherical environment, the standing wave will not form so well. However, as it turned out, in the first version we had 8 ultrasonic transducers, 4 on the bottom and 4 on each side, or 1 on each side. So in the spherical version, we could use only 3 transducers and get even more power and more sonoluminescence, just because a sphere is a lens, and it's both an acoustic lens and also an optical lens, because when it's filled with water, it becomes a huge, perfect lens, and it also magnifies the phenomenon itself that you're looking at, sort of like this very old water lenses that they put in front of first television sets, which was a very fanciful device, I think.
We'll show you a little video fragment of this piece, because the static images, of course, don't do it proper justice. Well, nor does the video, but that's a different story.
And when we saw the sonoluminescence for the first time, of course, we didn't know how the sound will look, and of course, we didn't see any sine waves or anything of the sort. And we were quite surprised to see rings, kind of toroidal structures and spirals, and these kind of structures that you would never see described, describing the sound propagation. So we'll let you.
Can we dim the lights a bit?
So, of course, Dmitry and myself, we were always interested in quantum physics because this is the most speculative and far-fetched, practically non-applied area, together with astronomy, of contemporary science. And but we could have never thought that we'll be able to create artworks that can give a viewer an experience of quantum reality or quantum sensations. However, the work with sonoluminescence and with camera lucida, which is one of our works that has been shown a lot, and it is quite difficult to exhibit it because we try to automate the installation so it can work as a standalone piece, but it was impossible because sonoluminescence is such a non-linear phenomenon that you can never program some kind of a sonic sequence. It will always come to a point that the situation will stabilize and the sonoluminescence will go down. So we created this hardware where we can play with amplitude and tuning of each individual transducer, and we have 3 of them, and we do it in real time, being in complete darkness, where you don't, like, where you operate an equipment as a sort of a blind man, and the audience comes with you into a completely dark, cave-like space. And, of course, they have no idea what will happen. And just this experience of being in the darkness and completely erasing your outer shell and your regular experience of other people around you, and kind of going into this internal domain of sound propagation and this burst of light from the deepest crevices of space. It gives you kind of a very refreshing new experience. And a lot of people who've seen sonoluminescence, well, Frederick, you've seen it. Maybe you can describe it. But the most common, like, you could hear many types of comments, but the ones that were recurring ones were the comparisons to, of course, the universe and the cosmos, because there is this effect that you're looking very, very deep into space-time, like when you're looking at the stars and you see this light coming from far away in time, and here you see this light coming from very far away in space-time, from these very minute increments of space-time that usually we cannot perceive. So here, and the other was the metaphor of looking at your own brain and on the activity of your own brain. And of course, our senses are quantum phenomena, and a lot of them are tuned on quantum scale. So going deep into this kind of sensation and creating environments where, for example, with sonoluminescence, you get, we use 40 kilohertz. So it's 40,000 flashes per second, and each flash lasts
10 to the -9th.
So you're
much less than a billionth of a second.
So usually we cannot experience anything that lasts a billionth of a second, and if it's repeated 40,000 times, you still get very short period of time. But somehow this experience is very vivid. And you can tap into this kind of temporal resolution even with your untrained senses. But of course, you need some adaptation. If you walk immediately into the room and the installation is working, you will see nothing. And then after some time, this kind of fuzziness comes in, and then this fuzziness comes into focus, and then you even start seeing colors. And we were also taught that in the dark you don't see the colors because night vision is black and white, but it turned out it's not so true. And what you're seeing here is a photograph of 2-colored sonoluminescence that was recently discovered, and we would love to work with it, but
like the video that you saw and the photographs, in order to create 2-colored sonoluminescence created by one of the few scientists that still does this kind of research in his free time. is that it's, well, yeah, I mean, I guess we should start with the fact that sonoluminescence mostly occurs in the ultraviolet spectrum, so we just get a little bit of bleed into the human visual range. And, well, in this incredible case, as once again in the case of the photographs and video that you've seen, almost totally pure sulfuric acid was used, and that's, well, even far too dangerous for any kind of laboratory environment to have that much sulfuric acid getting sonicated or just even standing still in the room. And so, yeah, it's especially illegal in any kind of public environment. So, yeah, I'm afraid that these experiments with sulfuric acid will have to go about in secret as far as any kind of public display is concerned. That's the only way to do it these days because, yeah, it's highly, highly illegal. In order to do that, well, in order to take those photographs and get that video documentation, unlike for public purposes where we simply use distilled water, there was actually special ventilation that had to be used to prevent the fumes from the sulfuric acid from burning our lungs. But these are the sacrifices that one must undertake. So we go from micro bubbles to macro bubbles. This was a work in which a white laser beam enters the membrane of a soap film, and instead of going directly through the soap film as it would through most optical surfaces, it actually gets trapped by the soap film and begins to move through it as though it were moving through a waveguide antenna. And so this is something that allows us to observe microscopic and nanoscopic molecular dynamics within the soap film, and it also allows for a gigantic billion-fold magnification of these dynamics in the form of a spherical projection that we prefer to do in a planetarium dome environment.
And although we were not originally interested in bubbles, but somehow they keep popping up, coming in a lot of things that we experiment with, and we were interested to find answers on more fundamental questions that are in the ground of all scientific discourse, such as what is mass, what is charge, and these issues are very, very mysterious, and they're kind of the groundstones that themselves cannot be defined. And the bubble is this really interesting environment, and even there are some models of our universe that use a model of a bubble. So another very interesting topic that we came across in our search is temperature. So this is another very mysterious thing that allows you, that's exactly the reason why cold fusion or any kind of fusion cannot happen here in our environment. And later, the very last work we will talk about tonight is the work where we use super cold temperatures, about -200 degrees, where you can observe subatomic particles moving. They are constantly moving through the space and our bodies, but you can actually observe them. They can leave traces in such cold environments. So just this temperature, of course, we know that life requires very particular temperature envelope to develop, and if you go away from this very comfortable temperature for life, you can also go into the realms of pure energy, quantum phenomena, superconductivity, and all these completely mind-blowing realities that we never experience.
So, Sonolevitation, the performance that you will experience this evening, is something that perhaps also has a lot of mythology implanted therein. A lot of us have heard these ideas about the fact that it would not have been possible to build the pyramids of Egypt or any number of other ancient structures if it weren't for some kind of special skills that were mastered by by those that executed this architecture. And lo and behold, was it 2 years ago or so, we were in a place called Paestum in South Italy, formerly known as Posidonia. It actually has the largest intact Greek ruins. I think. Well, yeah, they're so well preserved that I think that you wouldn't even find anything quite as astonishing in Greece. And there, amongst the relics, we encountered this this vase here.
2,500 years old. And of course, no one knows what is depicted here, but it looks very curiously similar to acoustic levitation or standing wave entrapment.
I guess it is important also to mention here one of the important Russian myths, or maybe it wasn't such a myth. In fact, the whole space program and in general the kind of Soviet infatuation with space didn't just come out of nowhere. It was actually based on a philosophical movement that began at the beginning of the 19th century called Cosmism. And the cosmists were quite certain, the likes of Fyodorov or Florensky, that humans would soon find themselves in outer space. It really wasn't any kind of speculation or mythologization. It was just an obvious future that they were preparing for, and they had a very strong impact on the Russian avant-garde, the likes of Malevich, who was convinced that his suprematist artworks were a means to contain interstellar space and to allow the viewer to enter the weightlessness, of course, associated with interstellar space.
And of course, when most of the people witness this performance, it takes some time to figure out what is going on, but the obvious guess is that some magnets are used, which we would like to tell you is not the case. So these two metal objects that you see on the bottom is a transducer or speaker that emits 15 kilohertz wave. So we selected 15 kilohertz because it's on the border of audible frequency, and some people with worse hearing, older people, cannot hear it at all, and younger people find it very annoying. So, but you can still hear the frequency quite well, and yes, it's a piezo ceramic transducer on the bottom, and on top it's just a piece of metal, a reflector. And the whole trick is in the distance between the speaker and the reflector. And this distance has to be
it has to be even.
It has to be even number of half wavelengths. So it has to fit exactly the even number of half wavelengths. And then when it comes to the top, it reflects and it goes exactly and it fits exactly in the nodes of the wave. And it intensifies the pressure, the sonic pressure, many fold than it would be in just wave propagating in one direction. And these curious nodes, these areas, these are the areas where the sound wave will change its phase. There are little points of vacuum, of near vacuum, are created in these nodes or antinodes. And exactly in the same antinodes, exactly in the same places in sonoluminescence, that's where the bubbles are collapsing. So in a way, this work is a variation of camera lucida, just in the air, not in a liquid phase. So it's a very simple principle. You could read about it in most textbooks on acoustics starting from 1950s. However, when we approach some physicists and engineers to build such a device, no one was up for a challenge. And what they used in the 50s, they used these whistles. They used golden whistles and kind of pumps that.
Whistle that is used to get a dog's attention.
So because you blow in the whistle, you already create this air pressure enough for levitation. But of course, using piezo ceramics, you can have much more precision, and that's how we wanted to do it. And luckily, by that time, we've been already collaborating for quite some years with a scientist in Russia who built a lot of equipment for camera lucida. And in the beginning, he had a lot of doubts about our knowledge and how competent are we in the scientific research. But by this time, he had enough faith in what we do, and he built this device. And it's interesting because he's a great expert in ultrasound, but he never did anything with sonoluminescence or acoustic levitation because these things are very impractical.
Well, they might seem impractical to us here on Earth, but they're very practical in outer space, because in a spacecraft, as soon as you have a leak of a gas such as oxygen, it can cause a fire, and the only way to recontain that gas, since you cannot see it, and for that matter, the only way to recontain all kinds of gases and liquids and solids, in the form of powders, is by means of acoustic levitation, which is much, much easier in outer space when you're not competing with so much gravity.
But actually, the acoustic levitation is finding some very fanciful applications. For example, when you have to work with a very small amount of material or substance, and you cannot put it in a container because of gravity and this very active and dense environment in which we live, everything that you want to control has to be contained. And in some instances, containment is just ruins the substance. So in order to perform some chemical reactions or having very little samples of biological matter or sample, these reactions performed in acoustic levitators. And this is a very interesting experiment that hopefully we can work with, and we have a work that comes very close to working with this phenomena.
Little Snitch automatically denied outgoing internet connections from submit.info. Details can be reviewed in your Little Snitch configuration.
Is a droplet of liquid that is acoustically levitated. So first of all, it is a sphere. It's a prism. It's a resonant cavity. And the sound gives this extra amount of resonance, because as it's levitating is taking the sonic frequency upon which it is levitated. And if you shine a laser through this kind of levitating or vibrating droplet of liquid, the laser will intensify 40 times or more, depending on the conditions. So this droplet itself becomes a laser. It becomes a lasing device.
It actually works in accordance with the principle that perhaps many of us have encountered acoustically, something that is known as whispering chamber modes. Perhaps you have been in certain medieval structures where due to the curvature of the ceiling, you can hear people whispering quite a large distance away from you, almost without any kind of loss in amplitude. And that's kind of what happens to the laser, is that it enters this sphere here. I don't know if you can see that over here. And when it does so, it gets trapped, and then it starts to go round and round and round, and as it does so, just as it would in a lasing cavity, it begins to amplify.
This is a very interesting geometric quality of a sphere, that the radius of the sphere fits exactly 6 times around its circumference, so it's a perfect standing wave device. But with a liquid, it's quite difficult to get a perfect sphere in our gravitation. Yes, because the gravity makes this shape of a droplet. So to make it a perfect sphere, you have to levitate it.
So here you see some levitated spheres, although they're not levitated in the same way that we'll be doing our performance this evening. This is a kind of levitation that was actually discovered quite recently, where the sound is coming from below a bath of oil, and droplets of the same oil are ejected onto that same bath, but they never touch the bath because they are separated by a constantly regenerated buffer of air that is, of course, triggered by the sound waves coming from below. And so this film of air, this pillow of air, prevents the droplets from coalescing with the liquid as they usually would. And under these circumstances, the droplets actually bounce on this air-oil interface. And when they do so, they also gather into these geometric lattices in accordance with the closest packing of spheres. And also, you can see the wavelength of the sound that is coming from below. You know, the higher the frequency, the tighter the lattice, and vice versa.
So, interestingly enough, this phenomenon could be observed from 72 hertz to 25 hertz, which is quite well in the audible spectrum. So this is quite wonderful, because you can actually compose music with these frequencies and then play it on a sonic bass, and you will have all this. So these droplets, they will be exactly dancing to the music and exhibiting all this very strange behaviors, very unusual behaviors. Sometimes they are very orderly, sometimes they are really fighting for their place, and you can see that only one unit can fit there. And the most amazing discovery that, and of course you can see all this very beautiful optical phenomena, this shadows and kind of penumbras and auras that result from the spherical shape and a prismatic from the optical qualities of the sphere of liquid being a lens, a very perfect lens. But the most amazing discovery to us came when we were already working with this phenomena that still doesn't have any name, is actually that this object is the biggest object that exhibits quantum behavior. Maybe you have heard about the double slit experiment, which is one of the most famous experiments in physics, and the first time it was performed in 1801 by Thomas Young, and he just performed it with a candlelight and very thin paper, and he could see the diffraction pattern that appeared from the light of the candle, and he made his conclusion that light is a wave, it propagates as a wave. So that was more than 200 years ago that he proved with an experiment that light is a wave. And then later in the 20th century, this experiment was performed with the same result with an electron, which is already a particle with mass, because Thomas Young performed it with a photon, with a massless entity.
Supposedly massless.
So it turns out that the electron also behaves as a wave. And then this experiment in 1999 was performed with a buckyball, which is a very big molecule of carbon composed of 60 atoms. So it's quite a massive object with quite a lot of mass. And then the same result was achieved with this droplet. Of course, we understand we don't have any kind of particle here, that this droplet, it is not really a particle. However, this wave function that is provided by the sound that propagates the waves through the liquid, it makes this little piece of liquid behave as a particle. So you kind of see this model of a wave-particle duality propagating. So there is this underlying wave net, this kind of fabric, this kind of waving, vibrating fabric that is guiding all the objects in the universe and makes them look like particles, but they are not particles.
Well, actually, what led the Yves Coudet group based at the University of Paris to such conclusions that we're observing wave-particle duality here is that if we were just if you consider this droplet to be the particle, and you can see its wave-like structure below. In this case, you can see this kind of ring of light below each droplet. It would simply bounce in place. But because of the fact that the droplet can interfere with itself, just as a light source can interfere with itself when it goes through the double slit experiment, through two slits, and creates an interference pattern, in that same way, the droplet interferes with itself when it begins to, as Coudet puts it, it begins to walk along the wave. It begins to drift along its own wave, and its movements are as unpredictable as those which are encountered in all sorts of wave-particle duality experiments, as well as various, the Coudet group has done a very recent experiment where they're proving the kind of dynamics that occur near the event horizon of a black hole, this kind of Landau states, where there are these rotary functions that can obey no other rule than can be characterized by a wave that it is at the same time a particle. These are just a few illustrations of the double slit experiment and the way that it was applied to to these levitating droplets by the Coudet group. So from droplets back to microbubbles, we, ever since I guess the times of 10,000 peacock feathers and foaming acid, when we started using a white laser, we understood that using a white laser in a variety of different environments gives you some very peculiar extension of what we call, it's something along the lines of a prismatic depth perception. You're able to see far deeper into micro realms, not only in terms of spatial dynamics, but also in terms of temporal resolution, because unfortunately it's not the easiest thing to document. That's one of the reasons why you see this kind of stroboscopy taking place in the video documentation. But in an actual environment where the laser is illuminating, be it in this case microbubbles of hydrogen, or in the former case these levitating droplets, or crawling into the innards of a soap film. In all of these examples, the laser is also scanning. It is also it is a very high frequency light. In the former case, as in this case, it is actually a sheet of light that is that reaches frequencies that allow, frequencies in terms of flashes per second, that allow us to see the kinds of things that the naked eye would never be able to grasp with seemingly continuous light. And, well, this work actually is in many ways a ponderance about this pivotal moment when sunlight penetrated the seas and oceans of the earth, and when it does so, it causes the water to divide into its ingredients of hydrogen and oxygen, and most of the oxygen becomes the atmosphere of the earth. It leaves the water, whereas most of the hydrogen remains in the water, and this hydrogen, it forms the basis of all DNA bonds, of all living matter. And so this quintessential process of electrolysis, as it is known, is also, believe it or not, the very basis of photosynthesis, and the way in which plants also transform sunlight by means of electrolysis into energy that is oxygen based, and the hydrogen forms the bonds of the growth processes of these living creatures.
But also, most of our universe is weightless, and it's mostly filled with hydrogen. So we live in an extremely dense environment that is full. There is no empty place or space anywhere. And even in the solar system, the Earth is the densest body. So imagine the space, the universe, where it's freely floating hydrogen. And that's what we wanted to recreate in this installation, to observe this free coiling, the hydrogen clouds that constitute most of the universe. And of course there is light in the universe, and we used white laser that offers you the broad spectrum of light. And you know how NASA, they take all these photographs of space, and usually it's hydrogen spectrum or radio photographs, and of course they have no color. So they colorize them to add this depths, and because the color kind of helps us to perceive the three-dimensional structure of the object better, and sometimes they have to reconstruct this three-dimensional structure, and maybe it is not even very accurate. So in a way, when you light it with the laser, you can also crawl deeper into this very intricate landscape that is three-dimensional. And then again, every bubble is a prism that reflects the light in every direction and kind of lights up. So we'll show you a little video of this piece.
As we were developing hydrogeny, we also came across the fact that there's a great deal of research being done these days in the realm of artificial photosynthesis. Perhaps the most efficient possible energy source. And this quantum chemist Daniel Nocera at MIT, with the contraption that you see in front of him, powered by simply one glass of water a day, he gets enough energy to distribute all the electrical needs for his 3-story house. But that's another fascinating Pandora's box that perhaps has less to do with art and more to do with the need for utopian tactics.
And at the moment we work with a scientist from Vrije Universiteit in Amsterdam, Raoul Freze, who also works on creation of artificial photosynthesis and this little algae that is genetically engineered to work basically as a source of hydrogen as fuel.
The engineering, it's important to note that the engineering actually just has to do with being able to pack more of these optical cells together than is possible in nature. That's really the difference. And that's really where the architecture comes into play. I mean, as you can see in this micrograph here.
And of course, the amount of sunlight is very abundant. And Raoul Fraser, he quotes such numbers that sun emits in 90 minutes the amount of energy that humanity uses in 1 year. And he still doesn't have a working cell that you can buy in the store and power your house. But he says that in about 5 years, this could already be very feasible and working, and you can maybe buy one and power your house like that.
So here we return to clouds of a different sort than the ones in hydrogeny. This is a piece that also uses a white laser to penetrate a very, very, very cold what is known as a supersaturated gas. There are a variety of gases that when they become supersaturated, in other words, when they are bordering on a liquid, as soon as you get any kind of charge carrier moving through them, this charge will cause a trail of condensation to occur, very similar to the kinds of condensation trails that arise when a plane is flying through the sky. Except for here, instead of planes, we're looking at subatomic particles that are moving at nearly the speed of light. So, of course, there's quite a bit more dynamics. But what is particularly shocking is that, indeed, as Evelina had mentioned before, what we usually perceive to be empty space, the so-called vacuum, is actually a plenum. Full of a vast variety of different entities, entities that one might call particles, but then if you take into consideration that they can quickly transform into other particles and into one another, perhaps this discredits their existence as independent entities after all. And most of what we see in this this chamber and this particle accelerator is actually coming from all reaches of outer space, and the really high energy, super fast particles, which are moving far faster and have far more energy than anything produced at CERN, in the Large Hadron Collider. Some of them really hundreds of thousand times faster. These don't really have any kind of even hypothetical physical mechanism that we can conceive of, which is why a lot of scientists have tried to trace down their vectors to supernovas and active black stars, black holes. And we can take note of the fact that when they hit the atmosphere of the Earth, when one of these super fast pions or a gamma ray burst hits the upper layers of the Earth's atmosphere, known as the ionosphere, they break up into billions of other particles. So by the time they get into our supersaturated gas, they have gone through quite a few transformations already, not to mention the kinds of transformations that they've gone through on I mean, in some of their cases, they have been traveling for up to tens of millions of years, trapped within the magnetic fields of our and other galaxies on the way.
And the modern day observatory of cosmic rays is situated in Argentina, and it's called Auger Observatory. And if you're interested in cosmic ray study, I recommend you to look at this very fanciful. It's kind of a CERN scale structure. It takes the space of 30 times size of the city of Paris, and it has more than 1,000 tanks that register its particles, because the most energetic ones, they arrive with a frequency of 1 particle per square meter in 100 years. So you really have to take a lot of data. But the interesting thing that then when they create these particle showers that you see here, that they only go 1 degree off the original trace. So even after a couple of decades, you can still pretty much close to the point of origin, to the vector of origin, and they all come from more or less the same parts in the universe. But the whole setup of this observatory is so far-fetched and utopian and fantastic, though I really urge you to look into it if you are interested in cosmic rays. And one of the scientists in the beginning of the 20th century, and he was a Nobel Prize winner, Millikan,
He won the Nobel Prize for determining the exact charge of an electron.
Yeah, and he was looking with his eyes on these condensation droplets, and for 11 years doing this like super precise experiments, and he was observing these traces, and he got so deep into it that he called them, he was trying to analyze what it was that he was observing, and he called them God particles.
That was the end of his career.
Yes, because really, when you look at something like this, even if you are a very cold and scientist and with a very sober mind, you can get carried away.
You quickly get intoxicated. Yeah. Well, yeah. I guess it's just an extra note here, but the way that they're registering these particles at the Auger Observatory is in water. It's through a phenomenon known as Cherenkov radiation, something that you can also see when you put radioactive substances, radioactive waste, for example, into a body of water. It begins to glow. Yeah. So, yeah, you can also observe these beautiful this kind of cosmic ray luminescence in water, and it can also cause the air to fluoresce, but the air fluoresces ultravioletly, and unfortunately, yeah, we cannot see it with the naked eye unless there are very special circumstances, and we heard about these circumstances recently. In case you find yourself in a cave, or for that matter, on a flight that is taking place at night, you can
to do it as high as possible. So the ideal environment would be a transatlantic flight where you're about 10,000 meters above the ground. And if you have a very tight mask that you can put on your eyes, and to be for about 3 hours in totally masked environment in darkness, these particles will be hitting your retina and causing kind of phosphan reactions. So they will be creating little streaks of light inside of your eyes. But of course it requires quite a meditation and concentration to observe it. But we were told by the scientists at CERN that this is another way to observe these subatomic entities. So we're going to try it on our next flight.
Can we turn down the lights? So if you have any questions, we would be happy to entertain them.
Now it's working. Yeah. So I was wondering the soundscapes of the movies. What kind of soundscapes are they, and have they anything to do with the processes you're working with?
The sound work is quite varied. I mean, in the case of Camera Lucida, the Sonochemical Observatory, it's quite direct. You hear the sounds that are not only causing the bubbles to implode, you're also listening to the bubble implosions themselves. And thankfully, unlike the sound that is causing the bubbles to implode, which we have to actually transpose into the human hearing spectrum since it's above it, the sound of the imploding bubbles is well within the human hearing range because they have plenty of subharmonics.
So Camera Lucida is is almost like a musical instrument, and this is what we wanted to be in the beginning. So you can play it. You can play with all and this is the only way to operate it. And we even did it with physicists at the Göttingen University when we were recording it in a bath of sulfuric acid. So we had to record many hours of footage for the DVD. So we were for 6 hours shooting, and 3 hours was the scientist operating the transducers, and he really got into it, and then us. And then in the case of mucilaginous omniverse and the work with silicon oil, we invited Son, Ivan Pavlov, who is a former Russian citizen now living in Sweden, and he is also a former acoustic physicist. So it's a great pleasure to work with him because he can really understand the whole situation from a point of view of science and really send very precise frequencies, and also not to forget about the other layers of sound. And in the case of the performance you will see tonight is mostly improvisation, and we have this one monotone frequency, 15 kilohertz. However, you will hear very different sounds because we use a contact mic that takes in real time the feed of how the pieces of gold interact with the standing wave, and how they change it and bend this existing very monotone sound. So you will hear it immediately. But of course there is no pre-recorded soundtrack for a piece like this. With in case with soap film and white laser piece, where we shine the laser through soap film. We worked for 4 years with Bas van Koolwijk, a Dutch artist, with whom we created together the software that in real time analyzes the behavior of the laser and the luminosity, the movement of the laser. And we have the soundtrack that we composed, and then this software in real time modulates the existing soundtrack to create more synesthesia with, so you have this really corresponding sound to what is happening. So, and in many of the works like Sonolevitation and Camera Lucida, we also try to tap into the physical life of sound wave and to show you sound not just as a musical composition, but also as a tangible phenomena that goes through your bodies, that through the air.
Yeah, I just wanted to make a note that I mean we are sound artists, but we also collaborate with other sound artists, just as we collaborate with other artists and scientists. I mean, we think that the creative endeavor in general should be as open and flowing as possible. Otherwise, you can't really reach the depths, I think, that are possible through a narrow mind frame.
Okay, thank you.
So you go very often and to work with scientists. What's the usual reaction when you arrive for the first time and explain your project and why you would like to work with them?
Well, I think that there are as many different scientists as there are other sorts of Homo sapiens. It's true, though, that many more of them are completely closed off from any kind of artistic, aesthetic approach to, be it their research or to anything else. But then, on the other hand, then there are scientists that are far more creative than any artist that we've ever met, and that not only are creative in terms of their scientific research, but they also might have hobbies, be it musicianship or a myriad of other creative outlets. But these are far, far fewer, unfortunately, and this has much to do with the pressures of scientific work. And this very fragile moment of encountering a scientist for the first time with whom you might want to collaborate it has to be very delicately choreographed, because I mean, after a while, somehow maybe you even develop an extra sense that allows you to know already upon your very first moments of discussion with the scientist as to whether there will be any kind of future collaboration possible, because it's there's a lot of intuition involved, but after all. Much of science, especially these days, unlike the scientists of the 19th century and earlier, there are not so many astronomers looking through telescopes, and there are not so many chemists doing live experiments. So much is just done through the lens of a computer. And this kind of separation from the senses is one of the reasons why many scientists are just far too numb for any kind of collaborative process. But then, thankfully, the ones that are not are the diametric opposite, really, understanding the value of the senses. But this devaluation of the senses is something that has been going on in science, of course, since the beginning of cybernetics, which of course also has its immense advantages, especially for science, but less for this kind of experiential approach to one's research.
You were talking earlier about the way some of your experiments can allow us to perceive time visually. Could you please elaborate on that?
Well, believe it or not, you could actually see a bullet flying in front of your face right now if you had a high enough frequency of light illuminating it. You don't have to you don't need to do it just with high speed video or film. It can be done in real time. Yeah. But it has to be very, very high speed in order to be able to see a bullet. It has to be on the order of hundreds of thousands of flashes per second. And that kind of thing is especially noticeable besides the laser works, which take advantage of this kind of stroboscopy, there's also the stroboscopy that happens in sonoluminescence. So you
the phenomenon itself is like a pulsar. It's stroboscopic. It's periodical, and because it's emissions of light, it behaves as a.
It has much to do with the functionality of the eye. The eye is always vibrating. In fact, there were experiments done in the early 60s by Ditchburn, wrote some very fundamental texts on optics in quantum optics in the 60s. Was also doing experiments with these vibrations of the eye, and if you can cancel these vibrations out with mirrors, you can cause a complete cancellation of vision altogether, and your brain goes blank. In other words, these vibrations are an excellent example of the fact that we can only sense the kinds of things that register a slight degree of difference in our perceptual field. And so when you have a bullet just flying in front of your eyes, of course you don't see it whatsoever. It's a blur. Maybe if you're very, very lucky and it's hyper illuminated, you'll see this blur in front of your eyes. But it is no longer a blur when you start to get into micro time. As soon as your flashes get very brief and very rapid.
So, no more question? So, we have a drink, and then we sonolevitate. Thanks.
Thank you.